Hello class, this is Tim Tomlanovich. Welcome to Learning Plan 2 in Water Technology. So with that, let's go through our slides. We'll go over some example problems and then you can do your practice problems. We'll discuss a quiz next then. All right, so let's talk about flow. Flow is the volume of water flowing past any given point in a pipe or channel per unit time. So in metric, typically it's liters per second, so capital L/S, or sometimes it's cubic meters per second, okay? So 1 cubic meter equals 1,000 liters, okay? In US, it's gallons or cubic feet per second or minute. So GPS, gallons per second, CFS, cubic feet per second, GPM, gallons per minute, CFM, cubic feet per minute. So on page 421 in your appendix, it kind of shows different units of flow rates. So typically, when you look at your water bill, they're measuring it in gallons. All right, so flow represents volume per unit time. So flow equals cross-sectional area times velocity. So Q, this is flow. That is your flow rate. Okay, Q. A is your cross-sectional area, and V is velocity, speed, velocity. Okay, area is in square feet. Velocity is typically in feet per, per second. Therefore, we are, if you take feet squared times feet per second squared, I get cubic feet per second. And then there's unit conversions to go to gallons per minute, etc. Okay. So let's do an example problem. Determine the required diameter of a pipe in inches that will carry a discharge of 10 million gallons, MGD, million gallons per day of water at a velocity of 10 feet per second, FPS. So given Q equals 10 million gallons per day. So we're going to start doing some unit conversions here. 10 million gallons per day, okay? Velocity equals 10 feet per second. Find the pipe diameter in inches. Okay, so we have feet here, we have gallons, we have day, we have seconds. So we have a whole bunch of mixtures of units. So the key to these problems is get consistent units, because you only divide, multiply, add, and subtract like units together. So we know Q, the flow rate, if it's a pipe and nothing leaks out, is cross-sectional area times V. So if we know if we know the velocity and we know the flow rate, we can take the flow rate divided by V to find area. And we also know area equals pi times d squared over 4. So we can back solve d, and then d equals 2r. So if we know area, once we solve for area, then we should back solve for d, diameter. Okay. So first, let's get our units consistent. So 10 million gallons per day. All right. So 336,890 cubic feet per day. Because if we know, so if we look here, we know 1 cubic foot equals 7.48 gallons. So if I take times 1 cubic feet divided by equals 7.48 gallons. So if I look, my gallons is in the numerator on this term, the gallons is in the denominator in that terms. That means I'm taking 10 million divided by 7.48, and that's when I get 1,336,890 cubic feet per day. Okay, so now we know times, I'm going to just go over here more, times So per day, so day is in the denominator, so we need the day in the numerator to cancel out equals 86,400 seconds per day, right? There's 60 seconds per minute, 60 minutes per hour, 24 hours per day. So you just multiply those out, you get 86,400 seconds. So now if you look here, the denominator, numerator, these cancel out. Now we're left with seconds. So our flow rate is 15.47 cubic feet per second. Okay. So now we rearrange this equation. Area equals 15.43 cubic feet per second divided by 10 feet per second. So if you look here, the seconds cancel out. Cubic feet divided by feet, we're left with square feet. We get an area of 1.55 square feet is the area of that pipe that I need to carry that flow at that speed. So now we know area equals pi d squared divided by 4. We solve for d. We put 4 times a divided by pi times the square root. I get 1.40 feet. Multiply that times 12 because I'm asking for the answer in inches. So I need a pipe diameter of 16.9 inches to carry 10 million gallons per day at a velocity of 10 feet per second. All right. So Q equals V times A. So let's look at example 2.7 in your book. Water is flowing with an average velocity of 4 feet per second in an 18-inch diameter storm drain. The pipe is flowing full. Compute the flow rate in cubic feet per second. Okay, so I got a blank. So first things what I recommend is write down what the problem is giving you. The water is flowing with an average velocity. So we know average velocity equals 4.0 feet per second in an 18-inch diameter storm drain. D equals 18 inches. The pipe is flowing full, so it's full, so that means we're using the whole area, cross-section area. Compute the flow rate in cubic feet per second. Flow rate is Q. Flow equals flow rate. Okay? So we know, so these are what the problem gives me. This is the question right here. Now 3, we know Q equals V times A. So it's asking for flow, so we don't have to do any algebra here. So we know V equals 4.0 feet per second, and we multiply by the cross-sectional area, which is pi times, now we want to turn, see this is inches here now, but don't we need that in feet? Because we have feet, see flow rate. We want asking for cubic feet per second, velocities in feet per second. So we gotta change the diameter into feet. So that equals 18 divided by 12. So that is 1.5 feet. So make sure you're in like units times 1.5 feet. We square that, the diameter squared, divided by 4. And I get a velocity of 7.1 cubic feet per second, or CFS. Again, write down what was given. Okay. Write down what the question is asking, and then solve it. And the key is consistent units. Okay. Consistent units. All right. Okay. So that was example 2.7 on page 30 of your textbook. All right. Continuity of flow. So now we know flow equals velocity times area, cross-sectional area of the flow. So as water is considered incompressible, so flow rate must be constant in any given section in the pipe, no matter how the velocity or flow area may change. So basically what comes in must have to come out. So if we change diameters, one of those variables has to change. So Q equals A1 times V1, which equals A2 times V2. All right. So if my cross-sectional area changes, that means my velocity has to change. If my velocity changes, that means, or if my velocity changes, then my area probably changed because Q stays constant. Q, just remember that when you do these formulas, Q has to stay constant. We're assuming that we have a closed pipe system. We don't have any leaks. So what comes into the system has to exit the system. So Q, the flow rate is constant. Okay. If Q is constant and Q equals A times V, when A gets smaller, that means the velocity must get larger. So think of a hose, your hose in your backyard. So what do? What happens when you put the thumb over it? We reduce the cross-sectional area. What happens to the velocity? It goes faster. Conversely, if we have a bigger area, if we make area increases, then the velocity slows down. So they're inversely proportionate to each other. Okay. So it's this math. So A gets bigger, velocity has to go down. A gets smaller, velocity has to go up to maintain the constant Q. That flow rate comes on. So as long as I don't touch that faucet knob and that flow is flow, it's the same amount of flow is coming out, cubic feet per second. So let's do an example. The nozzle below has a 3-inch diameter inlet and a 1-inch diameter outlet. So the flow is coming in, so Q in. And we have Q out. Okay. The flow rate is 5 gallons per minute. Determine the velocities in feet per second at both inlet and outlet. Okay. First, we need everything in terms of feet and seconds, so let's convert. All right, so we have 3 inches, 1 inch, 5 gallons per minute. So inlet dimension, 3 inches, 3 divided by 12 is 0.250 feet. Outlet dimension, 1 inch, 1 divided by 12 is 0.083 feet. So we got that in feet. 5 gallons per minute divided by 7.48 gallons per cubic foot. We get 0.67 cubic feet per minute, and then 0.011 cubic feet per second. Okay, so now we in cubic feet per second, feet, we're good. Okay. So when you do these problems, it's good just to try to leave as many decimal places as you can, because your answers will work out. So now let's find the cross-sectional area, inlet area, pi d squared over 4. We get 0.049 square feet. Put the d of the diameter in feet right there. Outlet area, pi d squared over 4. I get 0.0054 square feet. Okay. Now let's find V1 and V2. Remember, Q equals A1 V1 and Q equals A2 V2. So basically what we can do, okay, let's find V1. Basically we do this. There's our equation. You take Q divided by A1 equals V1. And then what we do is we take Q equals A2 times V2, because Q is constant no matter through there. So we take Q divided by A2, and that'll give me V2. So the velocity is changing. Velocity is getting larger because the area is getting smaller. So if you look at that, Q1 times A1 divided out, you get 0.224 feet per second for V1, and then Q divided by A2, I get 2.037 feet per second. Okay, so as you can see, area goes down, velocity goes up. Area goes up, velocity goes down. All right, let's do 2.9 and 2.10 in your textbook. All right, example 2.9. In the pipeline shown in figure 2 and figure 211, so this is figure 211, the area at section 1 is 0.5 square meters. Section 1. Okay, so let's write down what's given here. Area 1 equals 0.50 square meters, and the area of section 2 is section 2 equals 0.25 square meters. Okay? So it gave us area 1 and area 2. For Qn equals 1,000 liters per second, determine the velocities at sections 1 and 2. So we know Qn equals 1,000 liters per second. So Q out has to equal 1,000 liters per second. So there's our problem set up. So we'll go back and forth to this. All right, so we need to find V2. So we need to find V1, V2. So now Q1 equals Q2. Okay, so let's do some math here. So first of all, what we need to do, we have the areas. So I'm going to write the formula out first. So let's do that. 1, Q equals A1 times V1 equals A2 times V2. Okay. So we know area 1 equals 0.5 square meters. Area 2 equals 0.25 square meters. And Q equals 1,000 liters per second times 1 cubic meter, because we need to be, so we got it, it's usually cubic meters per second or cubic feet per second is the most common units we use for flow. 1 cubic meter equals 1,000 liters, so we're left with 1 cubic meter per second for my flow rate. Okay, so V1 equals Q divided by A1, and that equals 1 cubic meter per second divided by 0.50 square meters, and we're left with meters per second, and then we get 2.0 meters per second. Okay, V2 equals Q is the same, but now I'm in the smaller area. Okay, so the area is getting smaller, so that means my velocity is going to get higher than A1. Okay, divided by A2, so that equals 1 cubic meter per second divided by 0.50. Oops. I gotta go area 2, which is 0.25 v squared, and then I get 4.0 meters per second. So that is our velocity change, but our flow doesn't change. So this is 2.0 meters per second. This is 4.0 meters per second. Okay, so that is V1. Bigger area, smaller velocity. Smaller area, bigger velocity. So the velocity changes. So this is like going from section 1 to section 2 is like putting your thumb over the hose. It's going out faster. All right, so that was problem 2.9 on page 31. So it's just methodology, write down the formulas, write down what's given, make sure the units are consistent. It's a simple little formula here. Just remember Q is constant. All right, so 2.2-10 on page 31. For the branching pipe section shown in figure 2.12, which is what we're looking at, compute the velocity of the flow section C. So we need velocity section C, which is right here. Okay. In the 6-inch diameter. So we know that's 6 inches. We know this is 4 inches. We know this is 12 inches. The velocity in the 12-inch branch is at section A is 1 feet per second, and the velocity in section B in the 4-inch branch is 5 feet per second. Okay, so we need to find the velocity here. So QA, so if you look, remember, Q in has to equal Q out. So Q in, so which is QA, okay, has to equal QB plus QC. Okay. All right. So knowing that, so we have a velocity, we have a diameter, we can calculate the Q at A here, correct? Yes, we can. So that's our first step in this problem, because you can only have one unknown variable. So we have velocity, diameter, we can find QA. Then we'll solve this one. So then once we find QA, and then we'll move to the next section. Okay. So with that, let's start there. So I'll go to the next page. Let's find the area of section A. Oops, wrong way. All right, so let's find area of section A, which equals pi d squared over 4, which equals pi times, so it's 12 inches in diameter, section A, if I look at that, right there, which is 1 foot, because I needed to be in feet, divided by 4. That's a foot mark. And that equals, let's do that, pi. Where's my pi on this button? Pi divided by 4 is 0.785 square feet. So now I can find QA. Step 2, QA equals V at section A times the area at section A. And that equals, so the problem told us 1 foot per second, 1 feet per second, and multiplying it by 0.785 square feet. Okay. That equals 0.785 cubic feet per second. Okay. All right, so now we know QA equals 0.785 5 cubic feet per second. Okay. So now we know, let's see here. So we know, now what do we do? So we know the velocity and the diameter here. Can we back calculate the QB in here? Because we have two of the unknowns. So that's what we want to do next. So once we know the Q in pipe B, then we can subtract that from the Q in pipe A, and then that'll give us the Q in C, and then we can figure out our velocity in C. Okay, so that's what we're going to do. So step 3, we're going to find the Q at section B, which equals the velocity at B times the area at section B, which equals, so velocity is 5 feet per second times pi times d squared. So 4 inches is 0.33 feet. Square that, divided by 4, and we can get our flow rate at section B. So pi times 0.33 squared divided by 4 times 5, I get 0.428 cubic feet per second. Okay, so now we know QA equals QB plus QC. So therefore, QC equals QA minus QB, which equals 0.785 cubic feet per second minus 0.428 cubic feet per second. And that equals, what do we get there? QB, did I do that right? Let me double check here. I just want to check this velocity right here. Pi times 0.33 squared equals, divided by 4 equals, times 5 equals 0.428. Yes, cubic feet per second. So 0.785 minus 0.428. So Q in C equals 0.357 cubic feet per second. So 0.357. So 0.357. This is 0.428. So this plus this has to equal this, because QN has to equal QO. So now we know a Q, we know a diameter, and we can back calculate a velocity. So the velocity at point C equals Q, the flow rate at point section C divided by area at cross section C. So rearrange that basic formula. So that is 0.357 cubic feet per second divided by pi times 0. It's a 6-inch diameter right here, looking at 6 inches, and I got to square that and divide it by 4. So my velocity is 0.357 divided by pi times 0.5 squared divided by 4. I get 1.82 feet per second is the velocity in pipe C. That is the answer they were looking for. So the smallest diameter has the largest velocity. This one has the second highest velocity, and then this one has the smallest velocity because it has the largest diameter. So did we solve the question? It was asking for the velocity here. Yes. Okay. So kind of a step process. Knowing Qn equals Q out, get your unit consistent, solve it. Okay. All right. So because we can do this, V1 A1 equals V2 A2, which equals V3 A3, which all equals Q, total Q, right? Or this was A, this was B, and this was, or I'm sorry. So this has to equal the total Q, okay? So remember, they all equal the same. So just ignore what I was just saying right there. All right. And I do believe that is it for my lecture here. So with that, the homework is listed in Blackboard, so work on these problems. It's a fairly simple concept. Qn equals Q out, and Q equals velocity times cross-sectional area. Thank you for your attention.